So let's start the class today. It's about T flip-flops and JK flip-flops. Okay, so in the last class we learned about D flip-flops, and today we are going to see another two varieties of flip-flops which are known as T. T stands for toggle, and JK doesn't stand for anything. We'll see what JK is. They are the two inputs that are through which we control the flip-flops. Okay, so this we saw. Okay, we saw the edge triggered flip-flop, and it is one of the most efficient and economical. It uses very less number of gates. Okay, this is the flip-flop we studied in the last class. Okay, today I am going to introduce you to JK flip-flop and toggle flip-flop. Okay, so these are the schematic of the two flip-flops. This is known as T flip-flop, in which you have only one input, which is known as T. T stands for toggle, and the other flip-flop is J and JK flip-flop. This is also very popular flip-flop. It gives lot of flexibility in design. So you have J and you have K and Q dash. Okay, so these are the symbols of the two flip-flops. Now what about JK flip-flop? How does this work? Okay, this is the characteristic table of the JK flip-flop. Okay, when it is 0 0, right, when the input is 0 0, whatever is the previous state, that will be retained. Okay, so at QT, whenever the clock is going high, right, if it is 0 0, whatever was the data, previous data, okay, that will continue to be retained in this flip-flop for J is equal to 0 and K equal to 0. For J is equal to 0 and K equal to 1, okay, so it's no change there. For J is equal to 0 and K equal to 1, the output will toggle to 0. If it were 1, it will toggle to 0. If it is 0, it will continue to remain in 0. Whatever may be the case, whatever is the previous state, it doesn't matter. If you are giving a 0 1 output at 0 and K, so T is going to be 0. Okay, T is not time, it is which T? Okay, this small t. Yeah, here it is T. Okay, it is the T. This is corresponding to the time period T. Okay, so now so it becomes a you are resetting the flip-flop. Or when you have 1 0, so whenever the clock comes, irrespective of the previous state, whatever it is, it will be set to 1. Okay, and 1 1, so it will invert whatever was the state earlier. Now it will invert it to Q dash T. Okay, if it were 0 earlier, it will become 1, and if it were 1, it will become 0. So that is how the JK flip-flop works. This is the characteristic table. Anybody has got a doubt on what is the characteristic table of a JK flip-flop? Anybody? Is it clear? Can someone say yes or no?
Sir, can you yes, sir.
Pardon, I didn't get your question.
Sir, can you quickly go through once again?
Okay, once again, no problem. 0 0 means whatever is the previous state, it will be retained. Okay, this is a flip-flop. With each clock, the data is supposed to change, right, depending on the inputs. Okay, now if it is 0 0, when the clock, so it could be a positive, it's an edge triggered clock. First of all, we got to remember all these are flip-flop means it's edge triggered. Now when the positive edge of the clock comes, it will see what is J and 0. If it is both 0 0, whatever was the previous output, it will retain there. If it were 1, it will continue to remain in 1. If it is 0, it will continue to remain 0. Is this much clear?
Yes, sir. Yes, sir.
Okay, and then when the next, then it will continue to remain there till the next clock comes. Okay, again remember, during when the clock is in the level state, no, the output will not change. It's only during the rising edge of the clock. Okay, now again when the rising edge of the clock comes, okay, if it is if J is 0 and K equal to 1, irrespective of the state, it will go to 0. Similarly, when during the rising edge of the clock, and if J is 1, it will go to 1, and if both J and K inputs are 1, then the output will toggle. If it were a 0, it will go to 1. If it were 1, it will get inverted. Okay, both these two terminals will get inverted. Is it clear to everybody?
So what's Q of T plus 1 that you've taken?
T plus 1 means when the clock, the next state, this is the present state. On getting a clock, it will go to the next state. So this is just to relate between the previous state and the next state. Is it okay?
So like it's the Q of T plus 1, it's what will be
one more clock, after one more clock pulse. Okay. T plus
Sir,
yeah.
So the next stage, it doesn't mean that like the next positive edge case or the next negative edge case.
No, see, this flip flop, it could be either positive edge or negative edge. So the output would either change with every positive edge or it could change with every negative edge, right? In the case of D flip flops, we saw that master slave configuration. The example which I gave, it was a negative edge triggered flip flop. So the data would change at every negative edge. And then we saw one more purely gate based, in which the data would change during the positive edge triggered. Okay, it cannot happen at both the edges. So by design, you have, it will be configured for either positive edge or negative edge, which will be specified. Is it okay?
Okay, sir.
Okay. Vinayak, is JK similar to SR? No. See, the basic difference between a latch and a flip flop is the latch will is a level edge triggered device. That as long as that say S and R output is there, the output will depend on that. But a flip flop, the basic difference is it is based on a clock. Whenever the edge of the clock, the output would change. So the output will be captured only during the transition of the clock. Okay, it could be positive or negative. So that is the difference between a flip flop and a latch. Okay. So what is the character? This is the characteristic equation from this. Okay, it means J Q dash plus K dash Q. Okay, this is the characteristics equation. Okay, if you put J is equal to 0, Q is equal to 0, so you will get, what will you get? You will get Q. That Q T plus 1 is equal to Q. That means the next, in the next pulse, it will remain Q. Okay, so if J is equal to 0 and K equal to 1, right? So it will be, both will be 0. So the output will be 0. Similarly, if J is equal to 1, K equal to 0, right? So J equal to 1, so this will remain as an Q dash, and K equal to 0, this will go. So similarly, so you can try to fit these equations out here. Okay, so this is known as the characteristics equation. Okay, the most important thing is to this is just a character. You got to know how this JK flip flop works. Okay, what are the various states? If you know this, you will be able to design various combinational sequential circuits. Okay, so this table is important for D, for JK, and now the next circuit which we are going to. So this is the positive edge. Okay, now if this example, it will be pretty clear what is going to happen. Can you tell me, this is the positive edge triggered flip flop? So let's assume initially so during this, okay, since J is 0 and K is equal to 1, it is going to remain 0, right? And then till the next positive edge, it is going to 0. Okay, can someone tell what would be the next state? This is the positive edge triggered. What is going to happen?
Negative.
Pardon? Yeah.
No change.
Yeah, there will be no change. So it will continue to remain. And what about the next positive edge clock? What is going to happen?
Change to 1.
Yeah, J is equal to 0, K is equal to 1. So it, and the next positive edge, if you see, both are 1. Okay, since it is both on 1, it will toggle from 1 to 0. Okay, if this much is clear, you will be able to design various kinds of flip flops. Okay, various sequential flip flops we will be able to design if this property of the JK flip flop is well understood. Okay, so there is another flip flop which is known as okay, now this is JK flip flop, and how to make a JK flip flop if a D flip flop is given to you. Okay, so we will see what is the modification to be done. So this is the modification, extra gates which we need to put to make it as an JK flip-flop. Now see what happens if J is equal to 0 and K equal to 0. Okay, what happens? Okay, this is 0, so you have a 0 output out available here, right? So this gate is not there. This gate is going to be there because J is 0, K is 0, so this gate is going to be enabled. So what is the input which is going to be given here, right? What is the input which is going to be here depends on this line. Now if I trace it back, it is going to be Q here, right? So suppose this is at a 0 state, so you will have a 0 here, you will have a 0 here, you will have a 0 here. So or this is a 0 0, so it will be a 0 here. So in the next clock it will continue to remain 0. So if it is a 0 and J and K are 0, it will continue to remain 0. Suppose it is 1 here now. Now if it is a 1 here, so this 1 will be available here. Okay, K is also, we are talking of a case where J and K both are 0. So this is 1 here. So 1 1 will give here 1 here. So the moment the clock comes, you have a D1. So again it will write 1 over 1. So 1 is available here. So now you have seen if J is equal to 0, K is equal to 0. If it is 0, it is going to retain 0. If it is 1, it is going to retain 1. Is this much clear to all of you? Anybody has got any doubt? Excuse me. Anybody? Can you speak out? Anybody?
Sir, when do you use D flip-flop and when do you use JK flip-flop?
Okay. Actually, JK flip-flop has gotten more flexibility than a D flip-flop, so for design aspects. So when you make a combinational, otherwise it is more or less the same, only it has got slightly more flexibility, right? So for the next state, sometimes to make toggle circuits and all, we will see JK can be easily configured as a T flip-flop and all. So there are certain applications. So when we see the applications and designs, then you will see that JK has gotten little more advantage. It has got 4 different combinations, right? So either you can retain the previous or you can flip so the design becomes slightly easier. Okay, using D flip-flop. When we make the combinational design, okay, it is slightly easier with JK. Okay, so
Excuse me, sir.
yeah, tell me.
So in this design that we just have over here,
Yeah.
how is like the circuit changing from a negative edge trigger to a positive edge trigger? Because that's the major difference we have seen between a D flip-flop and a JK flip-flop till now, right?
No. D flip-flop also can be made as a positive edge triggered and a negative edge triggered. JK flip-flop also can be made as a positive edge triggered and a negative edge triggered. Okay.
Alright, sir.
Okay, here we are giving the clock here. This is going to be a positive edge triggered flip-flop. Okay, there also we gave a clock here. It is going to be positive edge triggered. If we give an inverted clock here and there, both will become on the negative edge triggered flip-flops.
Oh, okay. So if we invert the clock, basically it will become a negative edge triggered from a positive edge trigger.
Yeah.
Okay, sir. Thank you.
So okay, now if you take another condition of J is equal to 0 and K equal to 1. Suppose initially it was 0 here. So J is equal to 1 and K is equal to 0. This gate is going to be disabled. This is going to be enabled. Okay. Now you are taking from Q bar. Okay. So if it is J is equal to 0 and K equal to 1, we are taking. Okay. So this will be disabled. K equal to 1. Even this is going to be disabled, right? J is equal to 0, K equal to 1, both this is going to be disabled. So it is going to be 0 out here, right? So whenever the clock comes, irrespective of the previous state, it is going to be set to 0 because it is a D flip-flop, right? If you have a 0 when the clock comes, is it clear? When J is equal to 0, K equal to 1, okay, you are going to get a 0 here, 0 here, 0 here. So D is 0. So whenever the clock is going from 0 to high, automatically this output will slave to 0, right? The next case is K is equal to 1 and J is equal to 1, K is equal to 0. So this is 1 out here. Okay, k is equal to 0, so this is 1. So both these AND gates are enabled now. Suppose the output is 1. Okay, so if it is 1, there will be 1 here. So this AND gate is available. So you have 1 coming from this path. So whenever the clock comes, okay, it will be slave to 1. Similarly, if suppose the output was 0 here, then it will be a 1 available here. So that 1 will come from here. J is 1 here. So you will have 1 coming from here. So in that case also, this is going to be slave to 1. Now the last condition is where J is equal to 1, K is equal to 1. Okay, J. So this gate is disabled. Right, this gate is disabled now, so you have a 0 here. Only path which is available here for D is this path. Okay, now in this path J is equal to 0. Now initially assume K is equal to if it is in a 0 state. If it is in a 0 state, Q dash will be 1, so that 1 will be available here. J is 1 and this is 1, so you have a 1 here. So with the clock it will toggle to 1. Suppose it is a already in 1 state in the next cycle. Okay, 1, so you have a 0 here, so that 0 comes here. So 0 and 1 will give a 0 here. It will be a 0 here. So in the positive edge clock, since D is 0, this is going to toggle to 0. So this is how this circuit will realize the required JK function. Is it clear? That's pretty simple, right? So okay, so we will see that okay, you will see that it's a D flip-flop is pretty simple. You are using 2 gates and 1 OR gate here and this. So JK is an slightly complicated versions of D. But when we make sequential circuits, you will see that you will see that when we see the design aspect, okay, the JK will be pretty easy. The combinational circuits required for various machines will be much simpler when we use a JK flip-flop. Okay, so why that is happening, that we will see when we design the sequential circuits. It will be pretty clear that JK circuits have gotten better flexibility, and it will give a much lesser number of gates will be required for making a big circuit with a specific function, right? Whereas D flip-flop designs will require larger number of gates. Okay, so but for certain applications this D flip-flop is also used. So in the market you will find both kinds of flip-flops being used, and it is readily available. Okay, so these are the JK flip-flops. Okay, the other kind of flip-flop, okay, this is, we already discussed this, so it's a repetitive slide, so we'll not go into that. Okay, the other flip-flop is known as the T flip-flop. Okay, T flip-flop is very simple. It is like if it is a 0, T stands for toggle. Okay, so if it is a 0, no, there is a mistake out here. T stands for toggle. Yeah, okay, sorry, okay, it's correct. If T is equal to 0, it will maintain the previous state. If T is equal to 1, it will toggle. Okay, is this aspect clear? If T is equal to 0, whatever is the previous state, it will maintain that. If it is a 0, it will continue to remain in 0. If it is 1, it will continue to remain in 1. If it is toggle input is given 1, that means okay, you are asking the flip-flop to toggle. So with every clock, 0 will become 1, and next clock 1 will become 0. So it will continuously keep toggling between 0 and 1. So that is why this is known as a T flip-flop. Okay, so the characteristics equation is like that: T XOR Q. Okay, you can see that if it is an T is 0, it is QT. If Q is 1, it is Q dash T. So the characteristic equation can be written as T XOR QT. In fact, it is not mere Q, QT. Okay, you can write that. Now how to design a T flip-flop? Okay, so the design of a T flip-flop is, you have a JK flip-flop, you give T out here, so you short this J and K inputs. Okay, so T is equal to 0, J0, K0. J0, K0 stands for same state, right? J equal to 1, K equal to 1 stands for toggle, right? So simply you can short the JK input and call it as T. So T flip-flop is realized like this. Okay, So you have positive edge triggered T flip-flops. So if you see, this is the T which is happening, and so every clock pulse, okay, the output is going to change. This positive edge triggered, the Q is changing. The next positive edge triggered, if T is 1, it is going to change. In this positive edge triggered, T is 0, so it is continuing to remain 0, right? Okay, so from D you can make an T flip-flop like this also. If you see, if it is you take a Q and an XOR. If T is equal to 0, we know what is this going to do. No, if it is a 0, it is going to pass the same state, right? This we have seen XOR gate. It's a control gate which we have done it even in our lab. If T is equal to 0, what will be available here? It will be available Q, right? So with the clock, the same state, if it is a 0, whatever is Q is available here. So D and Q, same output whatever was there earlier will be fed here. It will continue. Whereas if T is equal to 1, okay, what will happen is, when you give an 1 and the XOR gate, this gets inverted. So in the next clock cycle, right, if this becomes inverted out here, right, so the output will be inverted, right? So you see, again in this example also you can see the difference between a flip-flop and an latch. If it were a latch, what happens is, it will form a loop continuously. This will become 1, it will come here, it will become 0, again it will become 1. So it will continuously keep, if it is a level edge triggered clock, you will find it is oscillating between 1 and 0. The output will be full of noise only. So only this kind of circuits will function well only for an edge triggered flip-flop design, right? That problem of race around you will find here also clearly in this kind of circuits also. So that is why we use flip-flops rather than latch. Okay, so is this aspect clear? What was Asim's question? Sir, okay, previous slide. Ankita, what was the which previous slide? Okay,
Sir,
yeah.
in T and JK flip-flops, Q is dependent on time, but in D flip-flop, it's independent of time. Why is it so?
No, it is in D flip-flop. Okay, let me take so many questions there. Okay, now I'll take this first question first. Okay, what is the question? Can you repeat that?
In T and JK flip-flops,
Yeah.
Q is dependent on time. Like we have Q in Q of T, but in D flip-flop, it's independent of time, right?
No, it is in D flip-flop. If you want to write an characteristics equation like that, you mean to say, right?
Yes, sir.
There it is simply Q T plus 1 is an D. Whatever is D, that gets reflected there.
No, sir, I didn't get you.
In a D flip-flop, Q T plus 1, okay, doesn't depend on the previous state at all in a D flip-flop.
Yeah.
Whatever is D, that is being stored at the output.
Yes.
So
Yes, sir.
Q T plus 1 is equal to D there. D T plus 1.
Okay.
Okay. So
I mean,
this give the only problem is that is the advantage of a JK flip-flop, that for some reason if I want the previous state also, okay, there is a possibility of retaining using that as the next output. Whereas in the D flip-flop, the disadvantage is every time, okay, you need to for every clock, you have to give a specific input for the required output. Okay, whereas in JK flip-flop, for any reason, say I want to continue with the same output, so I can give J and K equal to 0, so it will continue with this. So that advantage is there in the JK flip-flop with
yes, sir. Yes, sir.
okay, so that is the advantage. Okay, somebody else has Ankita, what was your T flip-flop table? Let me go to JK flip-flop. Yeah, tell me what is the problem. You can speak, in fact. Want to write it? Okay, no problem. I have written it. Okay. Now, Syed, you had some. What does the circle on the second output means? Which diagram? Where did you see a circle? T flip-flop. Here. Where is a circle? Okay, here. Okay, this means it's Q dash. Okay, this is Q, this is Q dash. Okay, 0. Always remember, this is dash. This is an inverted output. You remember this always. Okay, Q and Q dash. Okay. Anybody else has got any doubt? Okay. So we saw this. We saw this. Okay. Now when we will start designing the sequential circuits in the next class, but I am just introducing you some few slides. I am going 2-3 slides. I am just going to show you. Okay, and discuss few small things. Okay, there are two kinds of machines. Okay, one is known as the melee type. Okay, what happens in this? If output changes, if the input change during the clock cycle, right? You have a memory. The memory state is dependent on the clock, whereas the output, you have one input directly coming to the output. So even when the clock is not changing, if the input changes, the output changes here in this. Okay, only whatever is the previous stage, that depends on the clocked circuit. Okay, so these are known as the melee type designs. Okay, you have another which is mostly used, which is known as the Moore type. In this Moore type, okay, if the input and there is a combinational logic where you have an input and you have a previous memory which is registered, that is also there. Based on this, a new combinational logic will be there and the output is taken from here. So this output will change only with clock. Is it okay? This is only the difference. Right now it might appear very vague. So just remember, there are two types of machines. One is melee, okay, in which the output will change with the input. Okay, if the input changes, even when the clock is low, okay, the output will change. It only uses, these machines will use a memory register, okay, to capture the old data, and this using this old data and the new data, new inputs and the old inputs, the output will be available. Okay, but when the input changes, this will also change immediately. These outputs also will change. Okay, whereas in the Moore machine, the input is available, right? Whenever the input changes, that input will be captured by the clock in one of the edges, and the output would also change only which is synchronized with the clock. So there are two kinds of machines which are available, which you are going to slowly learn about how to design these logic circuits. Okay, so just remember there are two types of clocks. Okay, so one of the machines which we are going to design, so you have QA QB. So I have 2 bits, so it's a 2-bit counter. So 0 0, right, 0 1, A is the LSB. Okay, then 1 0 1 1, and then it has to go back to 0 0, right? So this is a clock which require, this is a counter which we require to design. So how to go about designing that? So you have the states 0 1 1 0 1 1 and again back to 0 0. Okay, so the clock, so here the LSB is A and MSB is B. So the mistake which we make while designing, most of us, is, okay, we don't take care of the MSB and LSB. Okay, so you have to be very careful while deciding what is the MSB, and accordingly you can give a nomenclature and then design it accordingly, right? Okay, so this is one way of realizing it. If you see, okay, you have put an this is the first one, it's a toggle. Okay, you have given a clock here, right? what happens is with every clock this is going to toggle 0 to 1, 1 to 0, 0 to 1 and 1 to 0, and you have taken the Q dash and given to the clock to the next state. Okay, what does this means? Whenever this is going whenever this is going to make a transition from 0 to 1, okay, this is going to toggle, right, again from 0 to 1 and 1 to 0. So this is one way of, this is known as the asynchronous counter. Okay, now if you see here, okay, when is B making a transition from 0 to 1? When this is going from 1 to 0, that is the time it is making a transition here. Now here again it is making a transition, and what is that? Whenever it is again making a 1 to 0. So from these graphs you can clearly see that B is toggling every time this A is making a transition from 1 to 0, 1 to 0. Okay, A is making a transition from 1 to 0. So this we have to take care. If it's if it is a positive edge triggered, then if you take Q dash A, right, QA dash, whatever is that, so we will get a positive edge trigger at these instances, right? So we have used this. Okay, so so we have used it like this. We have put an Q dash here and we have given it here, right? So this is how this can be. So here what we have done is, if you see, this is another way of realizing it. It is a D flip-flop, it is a QA, so you are giving QA here, right? So what happens is, if it is it will toggle every time. With every clock it is going to toggle, because you have put an XOR gate here. If it is initially, if it were a 0 here, it will come 0 1, it will become 1, it will toggle. If it were 1 here, it will 1 1 0. So this will going to toggle with every clock. What about this? This will not toggle with every clock out here, because you have given a actually this clock should be given here. Okay, so again from Q bar this has to be given the clock here. So this connection is missing out here. So if you give this connection out here, this will also toggle, okay, because you have put in, but this toggle, this clock is being driven by a Q bar from here. So that is how. So this is an asynchronous counter. Okay, so if you connect this will work like an asynchronous counter. Okay, now you might be wondering, how did I design these things? There has to be some method, right? It is not arbitrarily you see a waveform and you start thinking. There has to be like for a conventional design, we had something known as K maps. Okay, using the K maps we made how to realize a function. Similarly in sequential circuits also, okay, if you want to make a counter, so how to get these XOR dates, how to get these data, so there has to be some procedure, right? And also like this counter is reading from 0 to 1 0 1, right? This is 0 0 0 1 1 0 1 0. Can I make a counter which will go to 0 1 1 and come back to 0? It is possible. Okay, can I make a counter which will read 0 2 1 3 0, not necessarily in the same order? Again, it is possible. Okay, so in the next class we are going to learn how to design. Okay, these are known as the sequential circuits. Okay, sequential circuits is nothing but the output is dependent on, when the clock is going high, the output should be dependent on the previous value which is stored. Like if it is 0 0, you are deciding, okay, in this case if it is 0 0, you are deciding it has to go 1. If for any other circuit, maybe for 0 0 in the previous state, you want the next state to go to 2 and then come back to 1. So that is why, so that is known as the sequential circuit design. Okay, so that aspect and how to use flip-flops and get various, it could be counter, states, outputs, and it could be various things. So all those things we will study from the next class. It will take 2 or 3 classes to learn about the design of circuits using sequential circuits. Okay, so that we will tackle in the next class. So we will stop it here for today. Is there any doubts till now? Anybody?
Sir, can you give some applications of flip-flops and counters?
Yeah. Okay. So application of flip-flop will be making a counter, right? And counter this is a counter which can read the frequency. So suppose you have a clock which is coming, right? Now you want to read what is the frequency of the clock. Okay, so you can make a counter and read the count. You can give it for a specified period of time and see what is the count, and based on that count, and you can say, okay, this is the frequency going to be, right? You understand? A counter can
So we use latches to build the flip-flop circuits, and to use D flip-flop to build T flip-flop, and we use T flip-flop for counters, right?
Yeah, not only T, for any sequential circuit, including a counter, is just one of the very small application of an flip-flop. Okay, now you will learn how to make adders. Okay, with the flip-flops and these things, we are going to make registers, and register way you can make adders, multipliers, which are more efficient than the 4-bit adder you have seen. You have seen a very big chain where it is made, right?
Yes, sir.
It can be
Yeah.
made when we use a sequential circuits. It you will find that those adders, multipliers, dividers we have not even studied, because it is going to be almost a very big circuit if you are going to make it with a combinational circuit. But divider, when we make with a sequential circuit, okay, it will be it will be a very small circuit. Okay, so almost every computation will be done in a sequential circuits only. Okay, all those combinational circuits are going to be a small part of the bigger circuits. Now once you read about registers, then we will see all the big architectures. Okay, adders. Again, we will revisit adder, and you will find the adder is so simplified. Multiplier is such a big circuit. You will find using the shift registers, sequential circuits, it has become so small. Similarly for multipliers, we even didn't touch the negative multiplication. What happens if you add and if you multiply? We just saw the signed multiplication, correct? Okay, we thought it's a positive. So if you try to multiply two negative numbers, it is going to be very difficult to use it. You can't just do multiply the way we did it there with the combinational circuit. So all those big circuits will be realized using these flip-flops. Flip-flops is just the building block. Okay, once we learn about registers, and after that we will take on these big architectures using with these what registers, sequential circuits designs. Okay.
Yes, sir.
Okay, is there any other?
So one small doubt.
Yeah.
Can we say that the QA here is positive edge triggered?
Yeah, this particular flip-flop which we have used is positive edge triggered.
And QB is negative edge triggered depending on QA.
No, if you see, let me go. This is a positive edge triggered, both of this individually, right? Now you are giving an inverted clock here, so you can call it that way, right? But
Okay, sir.
each remains a positive edge triggered. You are just giving a clock from Q dash as per our requirement, right? Okay, so we are using flip-flops to run flip-flops. Yeah, here that is known as asynchronous counter. Okay, the word asynchronous come because each every this clock and this clock, they are not synchronized. Okay, so that is why we have called it as asynchronous counter, and these kind of asynchronous circuits are rarely used because it has got lot of problems that we will see. Okay, we are going to study the design of circuits wherein we give the same clock to all the flip-flops in the circuits. Okay, still we will be able to make a counter in the next class. Okay, this is just to introduce you, okay, the applications, just to give a small insight into the applications. And since there was time also left in this class, I put these two slides. Otherwise, first we are going to learn about synchronous counters, in which we will assume that all the flip-flops will be given the same clock, but still they will whatever function we want to realize, we will be able to do that. So that design aspect we will learn. Is it okay? In the next class we will learn that synchronous design, and then we will also see a synchronous counter design also, and then we'll understand what is the disadvantage with this asynchronous counters. Okay, if there are no more doubts, then we will